Okay, let's dive into this. Welcome, team, to today's Threat Briefing Explainer. We're looking at a massive, fundamental shift in the threat landscape. Because think about it, the evolution of software engineering has totally transformed our CI/CD pipelines. It's no longer just some peripheral automation utility sitting in the corner. CI/CD is literally the central nervous system of the modern enterprise. And because of that, the engine of our delivery is actively under attack. Threat actors have figured out that compromising the build environment is hands down the most efficient path straight to production. So today we're going to unpack exactly how these attacks happen and, more importantly, how we lock down our infrastructure.
Here is the bottom line up front. The build runner, the compute node actually responsible for executing our pipeline logic, has inherited a level of privilege in network access that easily rivals or honestly even exceeds our production servers. Just look at this quote from a recent architectural analysis. Self-hosted CI runners are effectively mini production servers. They've got persistent network access to internal repos, sensitive caches, cloud provider metadata, and deployment credentials. The blast radius of a compromised pipeline it's massive. If an attacker gets a foothold here, they can exfiltrate secrets, move laterally across our network, or even inject malicious payloads directly into our software supply chain.
Which brings us to a rather stark question. If runners are production servers, why aren't we securing them like production? Right now, we're operating on this implicit trust model. Our systems just assume that code flowing from a version control system is legit simply because it came from an internal repo. But guys, this creates a dangerous blind spot. It's basically the modern Trojan horse. If an attacker compromises just one single developer's credentials or exploits a bug in an upstream dependency, they can hijack the runner's execution environment from the inside out.
Here is a quick look at the intelligence we're covering today. 1. The CI/CD attack surface. 2. The Shai-Hulud case study. 3. Poisoned pipeline execution explained. 4. Bypassing standard security. And 5. Hardening the build environment.
Section 1. The CI/CD attack surface. It's that dangerous intersection where developer trust directly collides with infrastructure authority.
Moving to Section 2. The Shai-Hulud case study. Let's look at a real-world example of persistent backdoors in action from November 2025.
Let's move to and see how this builds, stage by stage. Stage 1. After compromising developer machines using Trojanized NPM packages, the worm used stolen GitHub tokens to spin up a new public repository. It actually enabled the discussions feature to serve as its command and control channel, which is pretty clever. Stage 2. It requested a runner registration token via the GitHub API. Stage 3. It downloaded the official GitHub Actions runner binary, installed it in a hidden directory on the victim's machine, and named it SHA-1-Hulud. And finally, Stage 4. The runner executed, effectively creating a direct outbound initiated link from the compromised machine straight into the attacker's hands.
Now, you're probably wondering, how did this thing achieve persistence without getting caught? Normally, GitHub runner cleanup mechanisms terminate spawned processes right after a job finishes. But the attackers bypass this completely by simply setting the environment variable runner_tracking-ID to 0. Plus, they used native tools to run a script that configured the runner as a background system service via systemd. This sneaky little trick ensured the backdoor survived machine reboots and operated totally silently, just masking the attacker's presence within legitimate infrastructure.
Section 3. Poisoned pipeline execution explained.
So how exactly do attackers get their malicious code to execute in the first place? Well, we call it poisoned pipeline execution, or PPE. By definition, PPE happens when a threat actor manipulates the files that dictate how a pipeline operates, essentially forcing the CI system to execute their malicious commands. The attacker might not even have direct access to the build environment itself, right? Instead, they abuse permissions in the source code repository to inject their poison, completely redefining the pipeline's execution.
To break it down, the threat landscape for PPE is really divided into 3 distinct categories. First up is direct PPE. This is where an attacker directly modifies the CI configuration file, like a Jenkins file or a GitHub workflow YAML, to include a malicious command, maybe something to exfiltrate environment variables to their own server. Second is indirect PPE. Here, the pipeline config itself is protected, so the attacker targets files referenced by the pipeline instead, like injecting a reverse shell into a makefile or an npm build script. And finally, we have public PPE. This happens when an attacker exploits open-source repositories by submitting malicious pull requests from a fork, just hoping the pipeline will execute their untrusted code during the build process.
Section 4. Bypassing standard security. Let's look at exactly how they evade our defenses.
Once an attacker successfully poisons the pipeline, they seamlessly glide right past our standard defenses. Let's look at a pretty fatal flaw in how we configure Linux containers. To allow CI containers to build new Docker images, it's super common practice to mount the host's Docker socket, that docker.sock file, directly into the build container. And this brilliantly illustrates our own security oversight. The Docker API is completely unauthenticated. Any process that can communicate with that socket effectively has root privileges on the host machine. So an attacker executing code via PPE can just use that mounted socket to launch a new, highly privileged container, escape the sandbox entirely, and totally compromise the underlying runner host.
Another critical vulnerability we see involves cloud deployments on AWS, GCP, or Azure. These virtual machines have an instance metadata service, or IMDS, sitting at a local IP address, 169.254.169.254. Attackers routinely use server-side request forgery from inside a compromised pipeline to query this endpoint and just steal the IAM role credentials assigned to the runner. And with those credentials, they can directly access our cloud infrastructure and deployment targets. It's game over.
We also essentially hand attackers high-privilege access simply by how we configure our workflow triggers. Trigger events like pull request target run workflows in the context of the base repository, which grants access to secrets even if the code comes from some external fork. Similarly, workflows that process issue comment events without properly sanitizing the text are prime vectors for remote command injection. Trusting external inputs natively gives threat actors the exact execution runway they need.
Section 5. Hardening the build environment. Time to open up the Blue Team playbook.
Okay, we know the attack surface, and we've seen their bypass techniques. Now it's time for tactical mitigation. Here are your direct marching orders. First, restrict runner network access. You absolutely must use firewall rules like iptables on Linux to block the CIA agent from routing to that IMDS IP address. Second, implement strict deny-all egress filtering. Your runner only needs to talk to the code repository and package registries, nowhere else. Third, stop using persistent static secrets. Transition immediately to pipeline-based access controls using OpenID Connect or OIDC. This lets you issue short-lived, dynamically requested tokens that are tightly scoped to specific branches and environments.
Next, we have got to eliminate long-lived, persistent CI runners. Persistent runners just accumulate state, cache dependencies, Git credentials, and potentially hidden background processes. This leads directly to workspace contamination, where an attacker modifies a shared file to infect subsequent legitimate jobs. The defense here is adopting an ephemeral runner architecture. Every single build job must execute in a fresh, on-demand environment that is entirely destroyed immediately upon completion. Tear it down, kill the persistence.
Remember that fatal flaw of mounting the Docker socket we talked about a minute ago? Yeah, we have to stop doing that. So the crucial point is, we must upgrade to rootless, daemonless container builds. Tools like Kaneko or Builda execute Dockerfile commands entirely in user space. They build the image file system layer by layer without any privileged access whatsoever and without a Docker daemon. If a build gets compromised, there's literally no root access for the attacker to escalate to.
Finally, we have to acknowledge a tough reality. Standard Linux containers are not true sandboxes. Sure, they rely on namespaces and cgroups, but they still share the host kernel. For highly sensitive pipelines, especially the ones handling production deployment keys or AI agents, we must upgrade to micro-VM isolation. Technologies like Firecracker or gvisor provide strict hardware-enforced boundaries. An attacker who breaks out of the execution layer is stopped cold by a solid hardware virtualization wall.
We've covered a ton of ground today, from poison pipelines to ephemeral architecture. But I want to leave you with one final urgent question to take back to your desks. Based on everything we've just discussed, how many unreviewed, overprivileged pipelines are executing right now in our own environment? The engine of delivery is under attack, folks. It is time to audit our infrastructure, implement these guardrails, and lock down our runners before an adversary does it for us. Let's get to work.